Hello and welcome to the lesson Deriving or Differentiating Logarithms. Straight away, I'm going to assume that you know what a logarithm is. If you don't know what a logarithm is, find the video explaining it, because from the get-go in this video, I'm going to assume you know that it's the inverse of the exponential and that you have some basic understanding of log laws. So let's begin. The basic log is y equals log base e, which is Euler's constant, x. And graphically, let's try and get some straight lines here. Vertical axis y, horizontal axis x. It has an asymptote at x equals 0, which I'll draw in here as a dotted line. And the graph looks something like this. Much like an exponential reflected in the line y equals x. It crosses the x-axis at the point 1, 0. Now, when you differentiate the log x function, you get 1 over x, which is the interesting fact that connects logs to polynomials, because this can also be written as x to the power of -1. Now I'll draw that in red on the same axes. Don't confuse it with the log graph. This is just the dy dx graph. It looks something like that. And as you can see intuitively, the gradient of the log function is given by the red line, and it's steepest as x approaches 0, and it gets less steep as x approaches infinity, but it will never be a negative gradient, the basic log, which is reflected in the 1 over x function. Now, more complicated logarithms involve a coefficient in front of x. So I could have y is equal to log base e b times x. And the derivative, dy dx, is equal to, again, 1 on x. When people first realize this, it's actually quite puzzling. You think, why doesn't the b, the coefficient in front of x, actually affect the derivative? And I think it's best explained by going to the log laws. I can rewrite this particular function to the right as log e x plus log base e b. And when I find the derivative of this expression, it's 1 on x, that's the basic log, plus, well, what's the derivative of a constant? Log e b is a constant, b is a real number, b could be 2. That's simply 0. So that's equal to, again, 1 on x. I'll just firm up that 0. And finally, logs can take more difficult forms. I think here's the most complicated form it could take. Y is equal to a log e b x plus c. So a is a coefficient that sits outside the whole term, b is the coefficient effectively in front of x, and c is a translation in x. All very complicated, but in the end, the derivative is not that difficult. Dy dx is equal to, well, a always remains out the front, and it's 1 over x plus c. The translating coefficient c simply remains attached to x, so this becomes a over x plus c. And again, the b doesn't really come into play for many of the same reasons, or you can prove it the same way as I've done just above in this line here. And that you can separate it out and treat it as a constant. So let's do a few example questions to the right. We'll do an easy one and then a more difficult one. Okay. Let's start off with y is equal to log base e 2x. Since b is equal to 2 here, and it takes the form y equals log e bx, I can say dy dx is equal to 1 on x. A slightly more difficult example below that, y is equal to negative 3 times log e negative x. Now here it's important to realise that negative x is simply a coefficient of negative 1 in front of x. So b equals negative 1, dy dx is equal to negative 3, which would always remain at the front, times again just 1 on x, because this does take the form y equals log e bx. So this equals negative 3 on x, or perhaps if you wanted to write it another way, 3 on negative x, but I recommend the first way we wrote it just there. But perhaps the trickiest form you could see these logs in, and I'll use this to demonstrate why it's important to get it back into a recognizable form, like this to the left here, is this form here. Y is equal to 2 log base e 3 bracket 2 take away a half x. Now this is not, as we speak, in the form that we have to the left here. So let's get it in that form. We say this is equal to, well, the 2 remains out the front, log e 3, and then I'm going to take out a factor of negative 1/2, which means in the following terms I have to divide everything by negative 1/2. So 2 divided by negative 1/2, I'll do that way over to the right, 2 over negative 1 on 2 is equal to 4 on negative 1, bringing that lower 2 up to the top, which is equal to negative 4. So now I have negative 4, and negative 1/2 x divided by negative 1/2 is simply positive x. So now I can combine those two coefficients at the start together. 3 times negative 1/2 is negative 3 on 2. And since it's positive x, take 4, I can put the x first. Doesn't matter where the x is, but this gives us a clue. Now it looks much like the form we have to the left of the screen. And so it's very easy to deal with. Dy dx is equal to 2 times 1 on x take 4, or 2 on x take 4.